let's start with the next part of the chapter, that is power. So what is power? Power is the rate of doing work. Okay. So for an example, here are suppose two students and they want to climb up this staircase. So name of those students are Ajay and Vijay. So let's suppose this is a staircase. Okay, your home staircase only. So Ajay climbs up in suppose 1 minute and Vijay takes suppose 2 minutes. Then now Ajay has more power compared to that of the Vijay, because in order to climb up the staircase you have to do some work against the gravity, and Ajay is doing it faster compared to that of Vijay. So time is small, then power would be more, right? So power is equal to work done divided by time. We can say this is the average power. And if we want instantaneous power, so instantaneous power is rate of change of work with respect to time. Okay, rate of doing work with respect to time. So that is derivative of work with respect to time. So now what is work? Work is force times displacement. Okay. So now if you have a constant force, okay. So if you have constant force, you can take it outside. So what do you get? It is F multiplied by ds by dt. And what is ds by dt? ds by dt is equal to V. So power, the instantaneous power in general, we can write it as F times V. Okay. So even if force is constant, force is not constant. Instantaneous force, we can take it outside, right? Force at a particular instant has some particular value. We can take it outside. So power is equal to what? D by dt of F times S. And force is the instantaneous force. So you take it outside because it will have some value, some fixed value. So then it is just d by dt of S. So it's equal to V, right? Power is equal to F times V. Is this clear? Yes, no? Okay. So power, if we want to find out average power, then it is total work done divided by total time. Okay, so it's just equal to work done upon time. And if we want instantaneous power, then we have to take derivative of work with respect to time. Okay, so for a particular instant, force will be, force will have some value. So we can write work as force times displacement. And because force has some fixed value, we can take it outside. So power is equal to then F times d by dt of S. Okay, that is equal to force times velocity. Okay, so this is the formula of power. Then now we know that according to the work energy theorem, work done is equal to what? It is equal to the change in kinetic energy, or it is minus of change in potential energy. Okay, and that's why what we can say is power is equal to dw by dt, and we can write it as dk by dt. What is k? K is kinetic energy. Okay, because work done is equal to change in kinetic energy, and it can be also written as minus of du by dt, because work done is also equal to minus of change in potential energy. Is this thing clear? So now let us see some problems based upon power. And so we talked about the conservative forces. So there are some problems, okay, based upon non-conservative forces also. First, let's see them. Then we'll see the problems based upon power. Okay. So let's see this problem. A body of mass 1 kg is thrown upwards with a velocity of 20 meters per second. It momentarily comes to rest after attaining a height of 18 meters. How much energy is lost due to air friction? So tell me what we can do. Body of mass 1 kg is thrown upwards with some velocity. Okay. It momentarily comes to rest after attaining a height of 18 meters. How much energy is lost due to air friction. So you have this body, you're throwing it upwards, it goes to some height and stops there. So what can we say? The change in kinetic energy will be equal to change in potential energy, right? Yes, no. So it has got some kinetic energy at the bottom. Okay, it has got some kinetic energy at the bottom. Okay, at h equals to 0 equals to, I can say, potential energy at h. But now see, it's moving upwards, so its potential energy will increase, kinetic energy will decrease. But while it is moving upwards, it is also doing some work against the friction, air friction. Okay, so can I say that this kinetic energy is spent in increasing potential energy and also in doing some work against the friction? Therefore, the kinetic energy will be equal to potential energy at h plus work against friction, against, right? Okay. Therefore, kinetic energy at h equal to 0 is half of m into v square equals to mg multiplied by whatever, till whatever height it goes, plus work against friction. Okay. So now let's put the values, because we want energy lost due to friction or work done against friction. So we want W. So that will be just equal to half of mv square minus mgh. Okay, that is half of m is 1 and v is 20. So half of 20 square minus mgh. So 1 multiplied by 10 multiplied by height is 18. So this is 20 square, 400, 400 divided by 2 is 200, 200 minus 180. Okay, that is 20 joules. This is the answer. Option D. Is it clear? Next question. 300 joule of work is done in sliding a 2 kg block up an inclined plane of height 10 meters. Work done against the friction is. So tell me, 300 joule of work is done in sliding 2 kg block. So you have 2 kg block and you are sliding it. Okay. So let's suppose it moves from here till the height h. What will we work against the friction? See, this is simple. Total work will be equal to mgh plus work against friction, right? Total work is 300 joule. Mgh is how much? 2 times of 10 times of 10, right? Plus work against friction. That is, you have 200. Okay, so work against friction is 300 minus 200. That is 100. Okay, work against friction is 100 joules. So option C is the answer, right? This is simple. Let's see next one. A body of mass 1 kg begins to move under the action of time dependent force. F bar equals to 2t I cap plus 3t square j cap, where I and j are unit vectors along x and y axis. What power will be developed by the force at time t? So how do we find the power? No, not dA by dt. Power is dw by dt. Okay. So you have to remember the power, the instantaneous power formula, which is F dot V. Okay, it is force times velocity. Force is a vector quantity and velocity is also a vector quantity, but power is scalar. So it is a scalar product of force times velocity. So now we know force, we want to find out the velocity. So for that, now initial velocity is 0 because it begins to move. This is given. Okay, it begins to move under the action of this force. Okay, so if you know force, you can find out acceleration. Okay, so acceleration is force upon mass, right? So that is mass is 1 kg. That means acceleration is just equal to force. Okay, so 2t into I cap plus 3t square times j cap. Okay, divided by 1 means it's the same thing. So after that, acceleration is dv by dt. Okay, so this is dv bar by dt is equal to this thing. Find out velocity. Okay, so dv will be equal to, yeah, integrating this. So dv will be equal to this times dt, and therefore you want velocity. So integral of this thing from u to v will be equal to integral of this thing from 0 to t. Okay, so this is on left hand side you have v bar minus u bar, and that will be equal to, you have 2t I cap. So 2 times integral of t dt. So that is t square upon 2. 2 times t square upon 2. Okay. So lower limit is 0. That means we just have to put the upper limit, and that is t. So this thing times I cap plus 3 times t cube upon 3. Okay. Integral of t square. T cube upon 3 j cap. Okay. And then this 2 gets cancelled, 3 gets cancelled. Okay. And initial velocity, because it begins to move, initial velocity is also 0. So then we get some formula for velocity, we can substitute it here. Okay, so power is equal to, therefore we have power equals to force times velocity. So force is 2t I cap plus 3t square j cap dot, you have t square I cap plus t cube times j cap. Okay, so just multiply x component with x component, y component with y component. So this is t raised to 2 plus 1, 3, 2t cube plus, this is what, t raised to 3 plus 2. Okay, that is t raised to 5. So 3 t raised to 5. So this is the answer. Unit is watt, right? It is option, it's option B. Okay, so is this clear? Okay. Next one, a particle of mass m is driven by a machine that delivers constant power k watts. If the particle starts from rest, the force on the particle at time t is. So tell me what we can do. Okay. See, what we can do here is, you have power equals to, see, this can be solved in 2 3 ways. Okay, so I can write power equals to what, the change in kinetic energy divided by time. Okay, we can write it as change in kinetic energy divided by time. Okay, so it is final kinetic energy minus initial kinetic energy divided by time, and then you have constant power. Okay, you have constant power, and that is K. So I can write that KT equals to final kinetic energy minus initial kinetic energy, and it starts from rest, so initial kinetic energy will be equal to 0. Okay, and how much will be the final kinetic energy? It is half of m into v square, right? So why am I doing this? Because in all options you have time and you want to find out force. Okay, so you know that K is equal to F times V, right? K is equal to F times V. So if you find out, okay, K is equal to F times V, and you have K also there in all the options. So first let's find out V. Okay, so then I can say V square will be equal to how much? 2 times KT divided by M, and therefore V is equal to, you will have V equals to square root of 2 times KT upon M, right? And then we can find out this, sorry, we want to find out F. So therefore I will substitute V equals to K upon F in this formula. Okay, V equals to K upon F. So K by F equals to square root of 2 KT upon M. Okay, and from this you can find out relation of F with other things. Okay, so we can move this on other side, this thing on this side, this thing on other side. So what do we get? We get F equals to K multiplied by square root of M upon 2 KT, and that is K multiplied by, okay, so I can say this is square root of K square. So that K square and this K will get cancelled, and what do you get? You get square root of Km upon 2T. So this is your answer. So Mk in numerator, 2T in denominator, or T raised to half is there, so you can take it outside. Okay, so it will be in denominator T raised to 1 by 2, or if you want it in numerator, it will be T raised to minus 1 by 2. Okay, this is clear. So your answer is option C, right? So now see, if you have constant power, then the work done or change in kinetic energy will be just equal to power multiplied by time. So I think this will be the fastest way to solve this kind of questions. Okay, there are other ways also. So let's try one. Okay, so now let's add a page. Hmm. So you have constant power, and what is power? Power is equal to F times V. Okay, and this is constant. So if you take derivative of this, it will be equal to 0, right? Because it is constant. So if I take derivative of this, I get df by dt times v plus f as it is derivative of v with respect to t. This is equal to 0. Then I have df by dt times v plus f times dv by dt, and I want to find out f. So see, I have df by dt times v plus, here I can substitute dv by dt is acceleration, right? So I can substitute force upon mass. Okay, so this will be F times F on m, or it is F square divided by m. This is equal to 0. Okay, then I can move this on this side. So I get df by dt times v plus, not plus, okay, this is equal to minus F square upon m. Okay, and now I don't want two variables. So what I will do is I will remove v also, because v is also a variable. Okay, So I will remove V also, and so we are given with this is equal to K. Okay, constant power is K. So I will substitute V equals to K upon F. Okay, so let's do that. So it is equal to K upon F. Okay, so I can move this F on this side. Okay, or let me move the terms containing F on left hand side and the other variable, that's time, on the right hand side. So I have df upon f raised to 3 now, this f and f square, and then it's equal to minus 1 upon mk times dt. Okay, and now let's integrate this. So let's integrate this df by f cube from 0 to some value of f is equal to minus 1 by mk integral of dt from 0 to t. So this thing is f raised to minus 3. Okay, right, f raised to minus 3. What is its integral? F raised to minus 3 plus 1 divided by minus 3 plus 1. And what is minus 3 plus 1? It is minus 2, right? So f raised to minus 2 divided by minus 2 is equal to this thing, minus 1 upon mk times t. Okay, so now you can cancel out the negative sign. So you will get, this is f raised to minus 2, you want f. So this is 1 upon f square. Okay, so move that f square on this side. So you have f square is equal to, move these things on this side, mk upon t, mk upon 2t, right? This 2 is also there, and therefore f is equal to square root of mk upon 2t. Okay. Let's compare. Okay, it's the same thing, right? Mk upon 2t. This t was in the denominator. Okay, so as you can see, this will take little bit longer time. Got it? Yes, no? Okay, so if you have constant power, then if you have constant power, or even if you have variable power, that depends on time. So the best way to solve it is use power as change in kinetic energy. Okay, it is, if it is variable, then it will be dk by dt. Okay, so move that dt on other side. If it is constant, then it's simple, you have just final kinetic energy minus initial kinetic energy upon time, right? This is too much to remember, but still, okay, there is, actually this will take double, okay, amount of time compared to this one. Okay, straightforward way will take double amount of time. So this is straightforward actually, because power is constant. So what is power? Force times velocity is, it is constant. Then if something is constant, what can we do? We can take its derivative, it will be equal to 0, right? So this is straightforward way, but it will take some time. Okay, clear? Yes, no? Okay, let's move on to the next question. One coolie takes 1 minute to raise a suitcase through a height of 2 meters, but the second coolie takes 30 seconds. So second coolie is faster to raise the same suitcase to same height. The powers of two coolies are in the ratio. Okay, tell me. Okay, but you can just say it's inversely proportional to time. Because first one takes 1 minute, second one takes 2 minutes. Who is faster? Second one is faster, right? Second one is faster. So powers are in the ratio of first compared to first, second's power would be twice because he is taking half time. It is just 1:2. Okay. Next question. Car of mass m starts from rest and accelerates so that the instantaneous power delivered to the car has a constant magnitude P naught. Okay, so I have included another problem just to emphasize same thing. The instantaneous velocity of this car is proportional to. So tell me, what should we do? As I told, if you have constant power, okay, what you should do is constant power is P naught. It's equal to change in kinetic energy. If you have constant power, just use change in kinetic energy. Okay, you want instantaneous velocity. So, okay, it starts from rest. Okay, so it is kf minus ki divided by t. If it is constant power, this is very simple because it will be just difference in kinetic energy divided by time. Okay, right. If it is instantaneous power, then you have to take derivative. Okay, so the initial kinetic energy is 0 because it starts from rest, and final is half of mv square, which we can say is equal to what? P naught times t. So P naught times t is equal to half of mv square, and you want velocity. So this is simpler compared to the last problem. Move this on other side. So what do you get? You get 2 P naught t is equal to, or divided by m is equal to v square, and from that you get v. So v is equal to what? Square root of this thing. 2 P naught times t divided by m. Okay. Or you can say it is directly proportional to t raised to half. Okay, you can take this t outside. So it is 2 P naught upon m t raised to half. Okay, so it is option B. So this one is similar to last question. Actually, the difficulty level is equivalent because here, in case of last question, what you have to do, you have to find out velocity and just put velocity is equal to what? Power divided by force. That's it. Okay. All right. Let's see next one. A body projected vertically from the earth reaches a height equal to earth's radius before returning to the earth. Okay. Body moves till the height equal to earth's radius. So this is height h, which is equal to r, and then it returns to earth. The power exerted by gravitational force is greatest at highest position, at instant just before body hits the earth. It remains constant all through, and at the instant just after body is projected. So can you guess? It remains constant all through. Okay, why will it remain constant? Work is independent of path. Power is not independent. Power is, what is power? Power is force times dot product of force to velocity. Okay. So now see, think of velocity only. Okay, think of velocity. It will be highest here when it is released. Okay, when it is thrown up, it's highest. When it hits back, it is highest. Okay, right? So now gravitational force also changes, but just consider velocity, it becomes zero at this point. Okay, it becomes zero at this point, right? So power will be zero at this point because velocity is zero. Okay, it will be high at this point, but now see, when it is moving up, when it is moving up, the gravitational force is downwards and body is moving up. So power exerted by gravitational force will be negative, right? So it is lowest, you can say, because it is negative. It is magnitude is maximum and it's negative, right? Velocity is upwards when body is just thrown up. Okay. and gravitational force is acting downwards. Okay, so now when it comes back and hits the earth, at that point again the velocity is maximum, and gravitational force and velocity, they are in same direction. So therefore its answer is, it is just before the body hits the earth, because at that time velocity will be maximum, same as that of velocity with which it is thrown, but at this time the velocity and the force, they are in same direction, so this product will be positive. Got it? Yes, no? Okay, so it is option B, right? This is also simple question, I can say. Let's see next one. An engine, an engine pumps water through a hose pipe. Water passes through the pipe and leaves it with a velocity of 2 meters per second. The mass per unit length of water in the pipe is 100 kg per meter. What is power of the engine? So there is some engine, and you have water in this pipe. Okay, water is thrown out with some speed 2 meters per second. Okay, it is thrown out with the speed of 2 meters per second, and mass per unit length is given. So if you consider unit length equal to 1 meter, then mass is 100 kg. Okay, this is given. So what is power? So power, you can say, velocity is given, it is change in kinetic energy divided by time. It is half mv square, okay, divided by time, because initial velocity you can say is 0, and it is thrown out with some velocity. Okay, so when the pipe water enters the pipe, its velocity will be 0, and it is thrown out with some velocity, right? Yes, no? So I can say it will be minus, sorry, mv square, half mv square minus 0 divided by t. Okay, so then what is given? V is given. Is the mass given? Mass is not given. Time is given. Time is also not given. Right. But what is given? Mass per unit length is given. So what we can do here is we can do some adjustment. So we can divide by L, because mass per unit length is given, and we can multiply by L. Okay. So what will be L upon T? Covers distance L in time T. What's that? Velocity, right? Okay. So it is velocity. You have power equals to half of mass per unit length. So mass per unit length is given. Okay. So we adjusted this, okay, L, because mass per unit length is given, right? M is not given. That's why we divided by L, multiplied by L. Okay. So you have, this is V, and you have V square already. So you have multiplied by V. Okay. So it is V cube. So what do you get? Then you have to substitute the values only. So it is mass per unit length is how much? 100. V is 2, right? V is 2. So it's 2 cube. So this will be 8. 8 times 100 is 800. 800 divided by 2 is 400. 400 watt. This is the answer. Option A. Is this thing clear? Good. Next one. A particle of mass m starting from rest undergoes uniform acceleration. If speed acquired in time t is v, the power delivered to the particle is. This is by far the simplest question on power. What is power delivered in this case? So P is equal to change in kinetic energy, right? Kf minus Ki upon time. So time is T. Initial kinetic energy is 0. Okay. Final is half mv square. Half m, everything is capital, right? So this is the answer. This one. Okay. Okay. This is simplest one. Let's see next one. Water falls from height of 60 meters at the rate of 15 kg per second to operate a turbine. To operate a turbine. The losses due to frictional forces are 10% of energy. How much power is generated by the turbine? So now loss is 10%. Loss is 10%. So you are giving some power, loss is 10%. That means how much will be the resultant power? 90%, right? So you can say efficiency is the output power divided by input power. Okay, this term is known as efficiency. Efficiency of any engine is output power upon input power, or output energy divided by input energy. Okay, so this is efficiency, and it is 90%. Okay, so let's move this on other side. You have P out equals to efficiency multiplied by P in, and that is 90 by 100 multiplied by what is input power. So falls from the height. No, it's not 100. This is percentage. Okay, input power we have to find out. So water is falling from some height. Okay, so it's falling with some energy. Okay, so you can say potential energy at top will be equal to kinetic energy at bottom, and therefore I can say it is equal to mgh. This much would be the work done. This much would be the kinetic energy divided by time. Okay, so now you are given with the height, and it's falling at the rate of 15 kg per second. So what is this? This is mass per unit time. Okay, m by t. Okay, and therefore you have P out is equal to 9 by 10 times m by t is how much? 15 times you have g is 10 and height is 60. So 10 gets cancelled. You have 15 times 60. Okay, how much? 900. Okay, 900 times 9, 8100. This is the answer. Okay, or you can say 8.1 kilowatt. This is the answer. Okay, yes, no. All right, let's see next one. How much water pump of 2 kilowatt can raise in 1 minute to height of 10 meter? So how much water a pump of 2 kilowatt can raise in 1 minute to height of 10 meters? So this is simple. Power is equal to work done divided by time, and you are raising the water. That means what will be the work done? mgh. Okay, so power is mgh divided by time t. And then, okay, power is given and height is given. Okay, and 1 minute time is also given. So you can find out mass. Okay, how much water is pushed up. So mass is equal to, I can say, power multiplied by time divided by gh. So power is how much? 2 kilowatt. So 2 into 10 raised to 3. multiplied by time is 1 minute. Okay, time is 1 minute. So we have to convert this to seconds, right? 60 seconds. And G is 10, H is 10. Okay, so this is 10 raised to 2 and this is 10 raised to 3. So we'll have 10 here. If we cancel out with this thing, 10 times 60 is, okay, 10 times 60 is 600. 600 times 2 is 1200. Okay, so mass is 1200 kg. So what is the answer? Tell me. Answer is simple. Answer is 1200 liters. Why? Because density of water is 1 kg per liter. Okay, and density is mass upon volume. Okay, so you have mass upon volume. So rho is mass upon volume. Rho is equal to 1. That means volume is equal to mass only. Just unit will change. Right. So this thing we need to remember that density of water is 1 kg per liter. Okay. And density of other things are calculated with respect to water.